Hi everyone, welcome to lecture 11. Today we're going to talk about text classification and in particular how to use the NLP pipeline um, to, to do tokenization, lemmatization, segment segmentations, and other features that could be useful to do text classification. We're going to talk about a few examples. We're going to first start with the GAL competition, text classification, GAL competition, and then at the end, I'm going to talk about sentiment analysis and reading comprehension. Um, so there is something called kind of classical natural language processing and then deep learning, and it's very different how classical NLP kind of does classification and other tasks in NLP, and how deep learning does it. So in classical NLP, there is a lot of construction of features and feature extraction and very sophisticated pipelines. In deep learning, it's more about a large amount of data and having deep and sophisticated models. So So, what are some examples of text classification problems? So, one of them is sentiment analysis. So, you have a review of a book or review of a movie, and you want to understand if that review is positive or negative. One example here is this example I'm going to talk about for a little bit here. It's called a Quora question pairs, and the idea is you have two questions and you have to figure out if these questions have the same intent or not. So what is the problem with text classification? So what's the challenge with text classification? So you have a document, sentence or a paragraph, and each of the documents have different number of words, right? So how do we take all of this unstructured text and we compute a fixed number of features? Because so far the models we have been talking about, the algorithms for machine learning, they take a fixed number of features. So how do we take this text and compute features so that then we can feed them into a machine learning algorithm and learn how to classify text? So here is the example from Quora. I find this example pretty interesting. So you have two questions and you have to tell whether question 2 is a duplicate of question 1. You can think that a website like Quora, this is a pretty interesting and important problem because you don't want to have people answer the same questions all the time. So you want to point the person who is asking the question to a question that is similar or exactly the same as the one he's asking, right? So here are some examples. What is the step-by-step guide to invest in share market in India? What is the step-by-step guide to invest in a share market? So these are different questions. How can I be a good geologist? What should I do to be a great geologist? Well, those are the same questions, and so on. You get the idea. So how do we solve this problem? There are many interesting solutions in in Kaggle, in the web in general, and I hope that you read in particular this blog post that I'm pointing out here, in which this person goes into a lot of details into the type of features that he computed for this problem. So I'm gonna tell you about some of them. So first is it's just some very basic features like the length of question 1, length of question 2, difference between length, number of characters of question 1, question 2, number of words in question 1, number of words in question 2, number of common words in question 1 and question 2. Those are kind of very basic stuff. Then he goes into something that is called some kind of string distance. Okay, so this Levenshtein distances are basically measuring the difference between two sequences. So you think about these sentences, you can think about them as sequences of characters, right? So this distance is the minimum number of single character edits, that means insertions, deletions, or substitutions required to change one word into the other or one sequence into the other. So, and they have different versions of these distances. So here are some examples of some of them. So what this person did was to compute many of these different distances based on this idea. And those are some other features that he's using. Then he went into TF-IDF and SVD features. So what he does is he computes TF-IDF of each question independently or the union of the two. He computes TF-IDF and then SVD after that, and he does it in kind of different ways. And these are all features that he's going to put into his model. The other thing he goes and compute is the words movers distance. And this is based on word2vec embeddings. And this is basically the minimum distance needed to move a word from one document to another document. So here is an example. So we have these two documents. Obama speaks to the media in Illinois. The president greets the press in Chicago. So what are the distances between these? So what you have to do is to take Obama and try to match it to one of the words on document 2. In this case, the closest word would be president. And then you take speaks and try to match it to the closest word in document 2, which would be greets. And then you take media and you take Illinois. And again, you try to match it to something in the next document. And then you sum these distances, and that will be the distance between the two documents. And again, this is based on some pre-trained word embedding, like word2vec embeddings, right? So this is kind of pretty interesting one. So there are other things that people do. So people look at capital letters, at whether the questions start with R, can, how. They look at n-grams in different and some kind of TF-IDF weighted n-grams and compute distances that way as well. So finally, like this person in particular took all of his features and computed different models, logistic regression and XGBoost. And the best model was using a bunch of these features and give him 81.4 accuracy. To compare to basically his best model, which had 85% accuracy, and it was a deep learning model, very complicated deep learning model. So these features actually take him pretty far. Okay, so next I want to talk a little bit about what people used to do, optical NLP pipeline. So what are the steps that people take to process text, basically, and how you could potentially use some of the steps are necessary. Basically you have to tokenize to be able to understand the units that you're working with. Usually they're words or subset of words or characters, so you have to at least tokenize. But then there are other things that you may do to text that may be useful as features in your text classification problem. So we're going to go through some of those. So here are some of the things we're going to be talking about. So first we have to tokenize. So what is tokenize? Tokenize is just this task of dividing text into pieces that are going to be called tokens. And these tokens are going to be kind of the unit in which we're going to work with. This is going to be used to build a vocabulary that will be determine the input to the representation of our model, or the representation of our features. So tokenization is tricky. For example, here are two examples. You have the word O'Neill or the word Arendt. So how are we going to tokenize those? Are we gonna take the apostrophe and divide that? Are we gonna just keep it the way it is? So here are some of the issues that we have. So, and we have software like Spacey to do this type of tasks. And here are some examples. I have some examples on how to do a few of those things. So there is something called subword tokenization. So sometimes maybe when you do word tokenization, it's not great because a lot of the words that you have are not in your vocabulary. So recently, people have been using more our subword tokenization. So instead of doing unfortunately as a word, you would do unfortunately. So you would divide the word unfortunately into pieces. Um, so so let me tell you how to do that. So there's a very popular algorithm called byte pair encoding, and this is used by BERT, which is a modern NLP model. And the goal of this encoding is to find a way to represent your text with the least amount of tokens. So let's see how to do that with an example. I think it's better to do with an example. So you have this example in which there are 3A followed by a B, D, A, B, A, C. So on the first thing you do is your basic vocabulary is just that everybody is a character, okay? So you find all the characters that you have in this text. And the next thing you do is to compute the pair that appears more common, okay? And in this case, it will be AA, okay? So let's call this AAZ. Okay, so now you replace AA everywhere with Z, okay? And now you then find the next pair. The next pair will be AB. Let's call this AB Y, right? And then you write this, replace AB with Y, right? Then the next kind of pair turns out to be a ZY, and then you keep replacing the text that way, okay, until the desired number of tokens are reached. So then when you're going to, so this is how you compute the vocabulary, right? So that's, you compute a vocabulary, and then when you want to tokenize, what you do is you list all tokens in order from long tokens to short tokens, and you iterate through all the tokens and check if each token is a substring of a word, and you substitute that token. You replace the remaining subwords to so you go one by one from the longest to the shortest and replace all of the all of the pieces of your words with tokens. So after you tokenize, so there are different ways, as I told you, there are different ways to tokenize. One is with words, another one is with pieces of words. And after you tokenize, you can either basically just keep everything in your vocabulary, or you can, in some cases, just basically say, I am just going to use the words that are used at least 5 times in my vocabulary, or tokens that I use 5 times in my vocabulary. And then I'm going to substitute rare words with a new token that I'm going to call UNC. Okay, so and at test time, you tokenize your test text, and you're going to replace anything that is not in your vocabulary with the special token UNC. Okay. So the next thing that people do after you tokenize sometimes is this process called lemmatization, in which you basically take words to a base form. And people used to do this a lot in English. I think they do it much less right now. So for example, you have the word cat goes to cats, coding goes to code, writing goes to write, right? But it's still very important in languages like Arabic and Spanish. when may be useful to lemmatize as well. And okay, Spacie does this for you as well. Yeah, the next task that we may need to do is sentence segmentation. So you have say basically a paragraph, and maybe your model needs every sentence to go independently, for example, into the model. So you may need to divide your text into sentences. So how do we do that? So in some cases, there are some, in English at least, there are some tokens that are pretty clear that is the end of a sentence, but then you have a period, right? And the period this could be a sentence boundary, but could be an abbreviation or could be part of a number. So how do we decide where to end the sentence, right? So one of the things that you can do is you can do a binary classification, right? So you can say, well, you can have a decision tree basically saying whether to end after a particular token, whether to end your sentence or not. So how do we train a decision tree like that? Well, you give it a lot of labeled data, right? And then you just kind of train the classifier that does that. So you take some features from before and after the particular token that you're in, and then you decide based on these features whether you divide the text there or not. So here are some of the features that you can consider. So you can say the case right before or after your period, for example, upper, lower case, the number, if it is a number or not. So you can think about the length of the word before the period, and then you can figure out the probability that a word before that period occurs at the end of a sentence or at the beginning of a sentence, for example. So this could be some of the features that you can compute for this task. So then after you have done, you may be doing all of these tasks or some of these tasks, you may also need to clean some of your text. For example, do fix spelling, remove punctuation or not, lowercase everything, remove stop words. Actually, many times you do this even before you do tokenization. Maybe you can fix spelling before you do tokenization, or tokenize somewhat and then do fix spelling. Remove punctuation, lowercase, and so on. Remove stop words as well. So then you can think about other features like linguistic features. And here you have part of speech tagging. So it's basically trying to figure out if a word is an adjective, is a noun, is an adverb, or a verb. So that could be quite useful as well, because some words are much more important, like maybe adverbs, adjective, and nouns are more important for a particular task than many other words. So you can be doing part of speech tagging and select the words that you think are going to be more useful for your particular task. And Spacie, of course, does that for you as well. So another thing that is pretty important in general is this problem called name entity recognition, which you will be trying to solve in your homework. And as I told you before, this is going to find, for example, in this text, tagging persons, dates, location, and organizations. And that could be useful because sentiment can be attributed to companies and products. In question answerings, you're gonna see that answers are often named entities. So you could simplify your problem by first tagging all your text and then trying to figure out if any of the entities in this text is the answer to your question, for example. So yeah, so Spacey does this. So there is also this other task called dependency parsing, and basically this will tell you which word depends on or modify other words. This is a kind of a tricky task. Look at this particular example. So scientists study whales from space. Are scientists studying whales from space, or are whales from space, right? So this is a funny one. And you know, Spacey also will do dependency parsing for you. So text classification before deep learning used to be done kind of in the way I described at the beginning. So you go and compute like hundreds of features from your text, and then you apply, you know, logistic regression, SVM, random forest, gradient boosting, feed-forward neural networks to your problem. So let's study a couple of cases in which people did that. So the first one is sentiment classification. So one idea is that you say you basically get humans and get a bunch of words and ask humans to decide if some words are positive or they are negative. Okay, and so humans will give you example of the positive and negative words, and then you may have some text and give some weight to the words that are negative and some weight to the words that are positive, and try to use that to classify. Here are some other features that you want to compute maybe for sentiment classification. So you want to be careful with negation, because I didn't like is different than I like, right? So you want to actually be careful when there is a negation, because that would be very useful feature to compute. You can compute unigrams or words that appear at least say 4 times. You can compute bigrams occurring at least 7 times, and these are some examples from a paper. So I'm actually just kind of telling you about some examples that I read on a paper. Sometimes you can look at frequency, but you can just look at a feature presence, and in some cases the presence of the feature is better than the frequency in which that feature appears in the document. You can attach part of p tagging to every word. You can just, instead of using every word, just use adjective and see that how that works. You can also basically use the position in the document. So for example, maybe everything at the beginning of the document, like the title, is more important than something that happens in the middle of the document or at the end of the document. So you can just kind of use the position in the document as a feature as well. So and here are some experiments that people run, different experiments with different algorithms and basically simple unigram plus bigrams does pretty well in this case. Even unigrams do pretty well in this case. So yeah, so these are some examples of sentiment analysis. So let me tell you about a second example, which is reading comprehension. So here is an example of reading comprehension. It's kind of funny, this example, because you see this entity 4, entity 6, entity 9, and what is happening is that before we see this example, somebody pass a, so basically the example kind of looks more like this. So entity 17 is democratic, BuzzFeed is entity 30. So basically this example has been pre-processed with the name entity recognition algorithm from Google. So where you see that is entity is basically a placeholder for something that for an entity basically, and this problem has been simplified. So the idea is that there is a passage, a document, and a question, okay? And the way the problem have been simplified is that the answer that you want to rank different entities. So in this case, the answer is entity 6. So again, what happens is that you have a paragraph, and in this case, you know that the question is going to be one of the entities. So in this case, is like characters in placeholder, which is one of the entities there. Movies have gradually become more diverse, and you have to understand what is the placeholder, and the answer is this entity 6 in this case. Okay, this placeholder is entity 6. So basically, the way, one way in which people try to understand this question is by ranking different answers. So given a passage, question, and answer, you want to rank different entities that are the answers to this question. And I don't want to get too much into the fact that it's a ranking problem, because we haven't talked about ranking that much. It's not very complicated to understand. Ranking can be seen as a pairwise classification or regression problem. But more than anything, what I want to talk about are the features that people compute to solve this problem. And basically is like, these are some of the ideas: whether the entity occurs in the package, in the passage, whether the entity occurs in the question, the frequency of the entity in the passage, the position of occurrence of the entity in the passage, n-gram match, some kind of word distance, sequence co-occurrence, some dependency parsing. So basically, I just wanted to give you a flavor of how people deal with NLP before deep learning, and how the sophisticated ways in which people compute features to solve these problems. And I think there is still some relevance to these ideas and these features. Thank you.